all the way. So I'm at the University of Brasilia. Okay, I have worked with previous PhD students of mine that are now at the Federal University of Rio Grande do Norte and Federal Institute of Technology in Brasilia. So I acknowledge that, well, we're together. The aim of the presentation is like that, is a work in the setting of threatening fatigue, and we are proposing an artificial neural network model to predict the crack propagation kink angles. Later I will show this, and I'm not talking at this point about the whole propagation, but the kinks that the crack will suffer step by step, okay? But later we will also try to predict the crack propagation. I believe I must use the microphone to, I forgot the microphone to the, perhaps there's someone. Is someone listening? Because I can, yeah, it's better. Sorry. Well, then we are going to compare this model with some established, well-established theoretical models available in the literature for this type of predictions. And then, as I said, we will compare the whole propagation path of the crack with some experiments, okay? Well, my colleagues have already introduced the topic, so I will not be long here. Threading is a quite complex problem. This is the, we say the Disneyland of threading fatigue. You have threading fatigue all over the places here, a number of components in contact, in all of them threading at least 50 or more joints inside the turbine, experiencing threading fatigue, right? The problem is quite complicated because you have stress concentration, stress gradient, multi-axial non-proportional stress states, some level of damage at the surface caused by threading wear, early crack nucleation, and, well, sometimes microplasticity. So all types of problems that we know from the solid mechanics. So it's a quite complicated problem, and with a lot of applications in the industry, mainly at the aircraft industry. So the next 2 or 3 slides are the most important ones to understand the presentation, okay? The other ones you can sleep, but these ones, please keep awake, right? So what we want to do here, what's the main idea? I want to estimate this angle, the kink angle, in a certain stage of the crack. Every time the crack changes direction, I want to be able to estimate this kink angle, okay? And I will do that based on the K1 and K2, stress intensity factor 1 and stress intensity factor mode 2, right? So that's the idea. And I will use an artificial neural network to model that, okay? All the presentations focus on this idea, right? Right. This is the classical artificial neural network model. So we have 3 layers, okay? Input layer, hidden layer, and the output layer, which is the angle, the kink angle, kink crack propagation angle that I'm looking for. Well, we have talked a little bit during the lunchtime. The problem with the artificial neural network is that people who do not have solid knowledge about solid mechanics start putting anything in here as input variable, okay? So the model becomes a very strict. It works only for that thing, and, well, it's not the idea when you want to use artificial neural network. So it's good that you have a good feeling, mechanical feeling of what should be controlling the crack, in this case, the crack direction, in order to choose the proper input variables, okay? So in our case, well, don't don't be too much worried about this. This is classical sort of structure. You find this in MATLAB basic tools there. So it's ready. You don't need to work too much in here, but you need to know what you want to give as input variables, okay? In order to make it feel sensible and to be mechanically consistent. So in our case, so what we chose here. So we are assuming from the beginning that K1, right, and K2 are the main factors controlling this kink angle, right? And we are defining as our input variables these four x terms. You will see that x1 is the value, is K11, and K11 is the maximum value of the mode 1 stress intensity factor, okay? And K21 is the value of K2 when this guy here, when K1 is at its maximum value, right? In a similar way, K12 is the value of mode 1 stress intensity factor at the minimum value of the loading path, and its counterpart here in K2 is K22, okay? So K22 is the value of K2 when K1 is at the minimum. So why is it interesting? Because, well, we know that K1 and K2 are related, well, domains, the magnitude of the stress to the head of the crack, and we are assuming that the most important variable is K1, but it's also the crack path will be also influenced by the value of K2. The other interesting thing that we are capturing here is some effect of non-proportionality, because we take always the value of K2, or all right, at these two different instances, okay? And we normalize these input variables by an effective stress intensity factor, which is defined as the maximum value of the square root of K1 squared plus K2 squared, because it's easier to work in the artificial neural network with normalized values, okay, between 0 and 1. Okay, up to here? Let's move on. These are the classical models that are available in the literature, okay? So we are going to work with the maximum tangential stress. The maximum tangential stress, consider a material point ahead of the crack tip, and you want to find this angle where the sigma theta stress is maximum in time. So you are maximizing according to the material plane and also in time, okay? So this is the hypothesis adopted by the maximum tangential stress. We are also using the maximal tangential strain range that was proposed by our research team in Brasilia. Pinto was my PhD student, also supervised by Hazard. It was a joint work, a co-tutor work with the student. And well, in this case, we say that the crack will propagate from this point onwards at the theta angle, where the range of the normal stress is maximized. Okay, so in this case, as we are talking about range, it doesn't matter the time anymore, but the plane. So I maximize the plane where delta epsilon, sorry, will be maximum. Okay, so those are the theoretical models. So how we feed now is another. I like to use. This is another important slide. Okay, so keep away. Just more true. Well, this is how I'm going to feed the AAM, right? It's like that. I need an experiment okay? And in the experiment, I will get the dominant crack. And let me take one point here as an example where you can clearly see a kink of the crack. At this point, I will measure the X and Y position, right, of this point, and I will build a finite element simulation, okay, and to compute K1 and K2, right? I can measure this angle. So all my input variables are now given by this test. This is a single test, fretting fatigue test, carried out by Almeida. It's a previous PhD student of ours, doing fretting wear test. Okay, I don't have the fatigue load, or remote fatigue load, but I have all the contact loads there in aluminum 750. So if I repeat this to the other points, I keep capturing data to feed my artificial neural network, okay? So in here, you can see I will have a kink in here, another one in here, another one in here, in here. I have 4 points, right? To extract from this single test to feed my artificial neural network. Look the other one. So every time the crack makes a kink, I go there, measure the angle, compute by finite element K1 and K2, and feed the artificial neural network. So if I keep doing that, as I said, 1, 2, 3, 4. For this test, I could capture 4 data for my as input data for my A and N. And then finite element modeling, typical, right? I then, after the finite element modeling, I have the theta from the experiments, K1 and K2 from the finite element, and then I can compute all my input variables, okay? And now I will do that for all these materials available in the literature, right? If I consider all of these where we could measure this, carry out these measurements, we will have 140 data sets. We separated 150 for training and validation, and 25 for testing, right? This word sometimes is misunderstanding for the people who are working with AAN. We understand validation in our case as well, the data used to prove that your theory is correct. Here is not. This, the validation in here are some data, usually 10 to 20% of the training data that you separate just to avoid that the network is overfitted, right? But not to prove it's correct. To prove it's correct, you are going to use the 25 testing data. This 25, the artificial neural network never saw it. Never saw it. It was trained without considering this data, okay? So now results. I know my time is over. Nearly over. I gave you 2 minutes more. No, let's go. You can see here that what we have here, an estimated theta kink angle, okay? Crack propagation kink angle against the experimental theta angle, the actual angle, right? You can see the A and N are the blue ones. So you can see that the blue data is quite inside. Most of them are inside the plus minus 10 degrees error in the prediction. This is angle, okay? 10 degrees angle, 10 degrees, minus plus 10, right? And, well, the worst of them was the the worst of them was the maximum tangential stress method in terms of the classical criteria. Then now we simulated, using this, we simulated the crack propagation, right? Step by step, doing that. And here's the final result, and then I move directly to my conclusions. You can see that for that data from Almeida with aluminum 750, This is the real path, the experimental path that the crack, this is X and Y, okay? To get the direction of the crack. And you can see that the AAN is the orange one, okay? Behaves quite well. There are some analytical models here that also look reasonable, but they are less stable. You see that they keep doing some strange paths here, and the AAN is more following the general path of the whole crack. Okay, let me show you. Forget this Stoy. Okay, it's another model that we used as well, but I will. Time was not enough to talk about it as well. Here we have also data for pine mica, a colleague who works in France, and here again you can see that the AAN follows quite well. In here, she worked with a bulk fatigue load that Almeida did not, and the crack was always open here. It's a positive ratio, okay? In the other test, we have the contact mechanic loads, but you didn't have bulk fatigue load, right? So we believe that the case was a bit more complicated because the crack faces were always, well, touching each other as well. And the conclusions, right? So, in terms of the capability of predicting cracking angles, they provide better results than the theoretical models. In terms of the whole propagation, the AN model was better than the classical models when high compressive loads associated to the fretting phenomenon were present. But for situations where the crack remains most of the time open, the AN and the stress range model provide comparable results, okay? And of course, we did this, as you saw, for a range of aluminum alloys. We need to see if it works for different materials as well, because as I said, the advantage of the A and N is if it can be generalized for other situations and other materials, okay? Otherwise, it doesn't make sense to work with classical models. You need less data, you need, well, less material constants and so on. Sorry, Jesus, too. Thank you.